Afternoon, everybody. Good afternoon and welcome. Welcome to the Physics Colloquia series. In this series of talks, we gather world-leading experts in their fields to discuss the latest advancements. Today, it's a pleasure to have Ravi from the University of Pennsylvania, which Ainz is going to introduce.
Sure. Yeah, with pleasure. Okay, so we have today Ravi Sheth here, full professor at the University of Pennsylvania. Ravi graduated in Cambridge, UK, quite some time ago. Then he moved as a postdoc in Berkeley first, then to Europe at the Max Planck Institute for Astrophysics in Munich, and then back in the US at the Fermilab. After that, he was a staff member at the University of Pittsburgh, and then he moved to University of Pennsylvania, where he soon became full professor. And for a couple of years, he was also full professor at the ICTP Trieste, so we almost had him in Italy, but then he went back to the US. And for this week and in the past week, he was visiting professor here, holding a course in a PhD course for us in large-scale structural cosmology. And it's a real pleasure today to have him here for the colloquium. Please, Ravi.
Thanks, Enzo. I switched to this mic so it's not double. I think that's right. You can hear, yeah? So thanks. Yes, it's true. I was at ICTP for a couple of years, and I was very happy there. A Russian told me, a Russian scientist, you cannot be happier than your spouse. And my spouse was not so happy there, so that's why we went back to the US. So I will talk about stuff that I've been working on in the last couple of years in cosmology. Yeah? So I mainly do, before this project, I mainly did stuff that was more analytically based, modeling the connection between galaxies and dark matter, the full dark matter field. And this is much more numerically based thing. Yeah? So what I'll try to do in the first half of the talk is set up the physics background before moving on to the computer science side of it. Yeah? The work was mainly done by Farnick, who was a student at the time, is now a postdoc at Yale. And he's been working with Nikhil Padmanabhan at Yale. Roya and Bruno in Paris, they've worked on optimal transport for a while. In some fields, it's called Monge-Ampere-Kantorovich dynamics. And so they've worked on it under that guise. And Bruno's done the computer science that I'll make use of at the end of the talk. Okay. So I'll do the motivation first. Then I'll talk a little bit about what reconstruction is. And then I'll talk about how we actually do it with optimal transport. Okay? And then it turns out that the optimal transport framework is useful for many other projects, not just in astronomy, which I'll highlight here, but also in physics and biology and stuff like that I won't be highlighting. Okay. Just to make sure we're all on the same page, the universe was hot in the beginning. It expanded very quickly. It took some time. Eventually, this cosmic background was released. I'll talk more about the cosmic background because that will play a big role in this talk. Once the background is released, then it takes some time before you form the first stars. Then gravity really goes to work, clumps the stars into galaxies, and the galaxies into the large-scale structures that we see today. Yeah? So that's the big picture. And so the big picture is that we view, we're the observer here, and we're receiving light from further out. Light has a finite travel time, so the further away means we're seeing the universe when it was younger. And we don't see the photons that came from further back from the time of the cosmic background radiation. from when the universe was super young. So this is effectively the boundary that we can see with photons. The James Webb Space Telescope, this will see the light from the first stars switching on. The current galaxy surveys see the light from galaxies somewhere here. Here is about when the universe was about half its current size. As the universe has expanded, has about doubled in size while the light has traveled to get to us. Okay, so that's just to set the scale. And one reason for setting the scale is to show you that with the CMB, we have a surface, and the surface is quite big. And we can use the features that we see on the surface to determine cosmological parameters for a reason I'll be describing in a little bit. But our hope is to use the entire volume, not just the surface. Yeah, so that's the goal. That's the overriding motivation. Okay. So the cosmic background radiation. So that is, you have hot photons, they're traveling through the universe. The universe is hot, so the universe is ionized. The universe is mainly hydrogen, so the electrons are free, the photons are free to scatter off the protons on the electrons. Universe cools as it expands. Eventually, the protons are able to trap the electrons. When that happens, the photons, which previously were scattering off the electrons, now only the ones that have exactly the right energy to make an electron jump up or down, only those will interact. All the others will travel in a straight line through the universe, which means now from that point on, basically all the photons travel in a straight line. Okay? And we know how hydrogen works, so we know the temperature of the universe when this happened, 3,000 degrees Kelvin. Okay. And so the toy model is that you have photons that in the early universe, as they move around, they scatter off the electrons, but eventually the universe gets cool and they travel in a straight line. Right? So that's what you see up there on the slide. So now we want to ask, what does an observer see? Okay? So an observer sees the photons that reached them. So on here, you can see waves of red, blue, red, blue, red, blue. So that's supposed to represent a hot region and a cold region. Where it's hot, there are more photons and they're going out. Where it's cold, there are fewer photons. So that means the cold region loses fewer photons because it's gaining, whereas it's gaining from the hot region. And so there's an oscillation between hot and cold, hot and cold. Okay? But eventually, this stops because the photons can free stream. When this stops, then you can ask, were you in a region that happened to be hot or in a region that happened to be cold? And suppose you were in a region that happened to be hot, then that means that the photons that you receive will all be hot. So they'll all be short wavelength. And what that means is in whatever direction you look, the universe will look the same temperature, hot. Okay? However, as time goes on, you will receive the photons that were emitted from slightly further away. Just took longer for them to reach you. And so that's what this expanding circle is trying to show, is that as time goes on, you will start receiving photons from further and further away. And so as you receive those, you will start to see a pattern. You will start to see that it was hot, cold, hot, cold, hot, cold. And so your sky will no longer be one temperature. Your sky will now be a combination of hot and cold regions. This was a very simple example of a single plane wave. But if I have many plane waves intersecting from many different directions, it will be a more complicated structure on the sky. But what turned the three-dimensional distribution of hot and cold into pattern on the sky is this. Yeah, so this is the origin of the CMB that is not completely smooth. Yeah, hot and cold spots. Okay. So because we know exactly when it happened, the universe was 3,000 degrees, we know that the photons were pushing electrons around for a finite length of time before they stopped. And so that means the photons and the baryons were coupled for a short amount of time before the and then the CMB photon was released. And so there's a length scale associated with how far the photons could push matter. And they'll be pushing matter at not quite the speed of light because they're pushing matter, so it will be the sound speed. And it was hot, so the sound speed will be relativistic, so it will be more or less the speed of light divided by square root of 3. And then if there were more baryons, then the photons had to work more to push the electrons. And so the sound speed will be a little bit less. And so these are things that we can work out. Yeah, so they've been worked out. And that means that there's a length that we know that the baryons got pushed out to. And so we can look for that length. And this is useful because that length is like a standard ruler, and it's placed a certain distance from us, the distance that the CMB is from us. So it will look to us like an angle. And so the angle that it will have will depend on the curvature, the geometry of the universe. So if the universe is flat, then we should see, if the rod is this length, then if the universe is flat, we'll see a certain angle, but we'll see a different angle if the universe is closed, okay, for the same standard rod. And so this is the geometric use of the standard rod. And in this case, the standard rod is the size of the spots in the microwave background map. Okay? And so this is the size of the spots. We're just asking what's the typical size. If the universe is flat, then the rod would have a certain angular size. Whereas if the universe is closed, then we will see the spots as though they had a bigger angular size. Okay, so this is the way the geometry of the universe is constrained from observations of the microwave background. So this depends on how big the rod is, how far the rod is from us, and what was the curvature of the universe. Now, this is a signature that's imprinted in the sky from the surface of last scattering. Yeah. So you know which one is the actual size because you know that these were made by the photons pushing the baryons until the universe became 3,000 degrees. And then a cosmological model will tell you what was the age, how many years it took to reach this temperature. Okay? So you know the time, you know the speed, so you know the size. So you know the size in meters. Astronomers, so in kiloparsecs. But, okay. And so you know this size. And so then you measure an angle. And it's actually a little more work, right? Because you know the size. So your cosmological model tells you how long. So you know the size. Your cosmological model also tells you how far away it is from us. Given that the universe, today the temperature is 3 degrees, then the temperature was 3,000 degrees, so the universe has expanded 1,000 times. And now, in that 1,000 times, we can ask, how much did the universe expand? So how much further is this surface from us? Okay, so a cosmological model will predict the size and the distance, and so the expected angle. And so we'll ask which model works best. Okay. So because the cosmological model that best explains this, and the one that best explains this has a flat geometry, also predicts how far the surface of last scattering is from us. So it also predicts the expansion history of the universe since then till today. a nice consistency check is to see if it got the entire expansion history correct rather than just the distance to that surface, okay? And so what we're looking for is something that will provide a consistency check, or in medicine you might call tomography. You slice the universe up and you ask at each stage, is it behaving, did it expand the amount we expect? Okay. At each distance from us. And so, of course, for that, we cannot use the CMB photons. We have to use something else. And so the question is, does the galaxy distribution today have some memory of this? Okay? Of the fact that the baryons were pushed for a finite amount of time. Because then the baryons will turn into stars, and we'll see the stars. So if you want, the question is, does the distribution of starlight in the universe have some imprint of the physics which set the CMB? Okay, so that's the goal. And so here again is the cartoon of what happened. You start out, let's imagine that you had a region with a little bit more photons, a little bit more baryons, a little bit more neutrinos, okay? And a little bit more dark matter. And then as the photons go streaming out, they push the baryons. They don't interact with the dark matter, so the dark matter stays, but the baryons are pushed. Okay? But they're pushed for a finite time, and then they're not pushed anymore. And so that means if there was an initial spike, then there should be a little ripple. And we know that distance. Okay? So if there was such a ripple, then this little ripple should be a slight excess of baryons around any spike in baryons. So if the baryons then turn into stars, which are galaxies, then around any galaxy, there should be a slight excess of galaxies. Okay? And so we're looking for this kind of signature, except it's complicated because there's not just one spike, there are many, so we have to do a statistical test. We don't know where the center of each circle is, right? So we just do a statistical test to see if it is consistent with this picture, okay, to see if this scale pops out in the galaxy distribution also at late times. And for now, we have to cross our fingers, right? Because it's 14 billion years from the time of the CMB until the present. And so we're hoping that that little excess of baryons leaves some signature 14 billion years later. Okay. The cartoon again, what do we expect to see? So if we look in the sky, then around each excess of galaxies, we should see a little circle. This is much more exaggerated than the real thing. The real excess is like less than 1%. Okay, so we had to wait till we had millions, hundreds of millions of galaxies to do this. So although this was realized in the 70s, it wasn't possible to do till the 2000s. Okay, so that's the cartoon, except the cartoon is a little bit wrong because there will be some galaxies that are close to us and some galaxies that are far away from us. And so this is appropriate for all galaxies at one distance. And so if we have a range of distances, then each one of them, the galaxies at one distance will make circles of a physical size that will appear as one angular size. And if they're further away, that same physical size will appear as another angular size. And then, just as we had to convert the angular size of the hotspots in the CMB, we had to compare that angular size with the physical size we expect to determine the expansion history between CMB and now. Now we do it between each galaxy sample and now. Yeah, so we're doing the same physics at many different times. So that's the cartoon. Okay. So that's the standard rod, right? That the length of the circle is like the size of the spots in the CMB, the radius of the diameter of the circle. This I just put up here to say we know how to calculate this thing. Okay? So don't worry too much. It's a bit of a pain because in cosmology, distances across the line of sight and distances along the line of sight, you have to be careful. They're a little bit different from one another. We know how different. In a cosmological model, we can write it down. But importantly, these differences, or how the distance changes with expansion factor, so the expansion history, that depends on what the universe is filled with, how much matter is in the universe. So if it's matter dominated, then, I don't know if I should try with this, but if it's matter dominated, then if I throw this up, it falls down, okay? So that the universe expands and recollapses. If it is filled with dark matter plus dark energy, it will expand, decelerate, and then the dark energy might take over and accelerate the expansion. Okay, so we think that our universe is filled with matter and dark energy. So this is the dark matter, and this is the dark energy. And they combine to determine the angular size of the hotspot given the physical size of the hotspot. And this angular size will depend on how far the galaxies are from us. So Z is our notation for how far away, how much the universe is expanded, roughly. Okay? So the thing I want to highlight here is there's this combination of, so it's the physical size, there's how quickly the universe is expanding today, and there is what the universe is filled with today. And then you'll get an angular size as a function of redshift. So what you're going to constrain with this method is some combination of this guy with this guy by measuring this at a range of redshifts. So let me show you that. Let me skip this one. This is just making the same argument. And of course, we're just a little technical. We're just careful about the fact that distances across versus along the line of sight. We're careful about that distinction. So we can define an isotropized distance, which is two perpendicular distances and one along the line of sight. Okay, so we have surveys like this, where we can do this over a range of redshifts, so over a range of distances from us. The galaxy surveys, and then further out, and then the CMB is at this number, Z is 1,000. Okay? So we're using these galaxies to make this measurement. So what do? You sit on a galaxy, and you count how many other galaxies there are at a distance r from you. If the galaxies were unclustered, you would expect 4 pi r squared dr times the number density. And then you will get some slight excess, or you'll get some difference from the expected random counts. So you take the correlation function, the ratio with respect to random, and you ask, what does that thing look like? So the pair counts, they look like this guy. And so what you can see is there's this spike at the scale of about 100 megaparsecs. And this 100 megaparsecs, I think on an earlier slide, I didn't go through and say what scale we expect, but this is the scale we expect. Okay. And so we're starting to see this in the data. We see this in two ways. The measurement I described, pair counts as a function of pair separation, or you can do the Fourier transform, and you can work with the power spectrum instead. The power spectrum instead, well, this is basically a smooth curve plus a spike plus a delta function. The Fourier transform of a smooth curve will be some smooth curve. The Fourier transform of that delta function, not centered on 0, will be an oscillating J0 Bessel function. And so the signal in the power spectrum looks like a smooth curve with a sine x over x sitting on top of it. And so the signature in real space, which is well localized to one scale, is spread out over many wavelengths, over many k modes in Fourier space. And the signal, so here what's happened is we've divided out a smooth curve to just see the oscillations. And it's the wavelength of the oscillation that is this scale. Okay, so although the two things are Fourier transforms of one another, the information is packaged differently. And so you're either looking for a very localized feature in real space, or you're looking for a wavelength in Fourier space. Okay, so this was the state of the art about 10 years ago. That we were able to see this spike. And so now the question is, let's do this for many different galaxy sets. So here is a bunch of measurements from the Dark Energy Survey instrument, so that released their data about a year ago. And so these are samples at a wide range of distances from us. So the bright galaxy sample is the closest to us, and then there's 0.4 to 0.6, 0.6 to 0.8, 0.8 to 1. So there's a bunch of different galaxy samples at different distances from us. And so the first thing to note is, well, what you really measure is distance in redshift and an angle for the separation between the pairs. So the first thing that has been done has been, if you want, to take the cosmology that we think is correct based on the CMB, use that to convert all angles into distances and all redshifts into distances. So when you do that, then you see that actually the curves all line up quite well. So that means our first guess at the cosmological model based on the CMB alone is actually close to consistent with the data. Yeah? So these are the raw measurements. So now the game is to turn these raw measurements into constraints on the cosmological parameters. And so then, okay, there's one more thing I wanted to show you. Sitting on here, these are measurements based just on galaxies. But it's also true that there's a sample here that are called QSO. So these are quasars. So the quasars are shining light to us. That light is passing through all the gas in the universe. And as that gas, as the light passes through that gas, some of it gets absorbed by the gas, depending on the chemical composition of the gas. Gas is mainly hydrogen. Okay. And so the light from the quasar is gradually absorbed. And we see a big forest of lines, which is the imprint in the spectrum of the quasar of all the gas between us and the quasar. And so we have like a one-dimensional skewer along each line of sight to each quasar of the gas distribution between us and the quasar. And so the gas is baryons, just not baryons that turned into stars. So we should see the same feature that we see in stars in the gas. Okay? And so that has also been seen and was also seen in this survey. And this is kind of a nice probe because the galaxies, we see them out to when the universe was half its present size. A little bit more than that. The Euclid satellite will see a little bit further. Okay. But the further they are, the fainter they are. And so the harder it is to detect them. Whereas detecting the gas in what's called the Lyman alpha forest, this is easier in the sense that you needed a bright quasar behind the gas. But then you're just looking for the absorption of the gas. So this is the way we'll see to even bigger distances, we'll see the baryon distribution. It's just in the gas, not in the stars. I mean, ideally in the stars as well, but we have a probe currently that's just the gas. And so we would like to see if that scale is consistent with the one from the galaxies. Okay? Importantly, because it's very different systematics, in addition to being further away from us. Okay? And so here are the constraints from fitting cosmological models to the measurements of the different samples that are all at different distances from us. Okay? And as I said, the thing you'll end up putting a constraint on is the combination of the Hubble constant times the length of the rod and how much stuff there is in the universe. And so what you can see is that the different samples, they will provide constraints with slightly different degeneracies between these two parameters because, remember, the degeneracy depended on the redshift of the sample. And so these are all at different redshifts, different distances from us, so you'll see the crisscrossing of the constraints. So the first thing to note is that they all kind of intersect in the same place. This didn't need to happen, right? So there is consistency. The different samples are consistent with the expansion history predicted by the CMB, or predicted by the model that was the best fit to the CMB. Okay. But you can also see that because we have so many different probes, as time goes on, each one of them will become a thinner banana and a shorter banana. And so they might stop intersecting with one another. And that will be the indication that something is not working with the standard model, or that there's some systematic in the data. Okay? And so where we're pushing is to be ready for the next set of data when these bananas are much smaller. Okay, so that's what I was calling the next generation data sets, right? Is when the bananas are smaller. Okay, so the size of the universe, so one way to plot those results is to say, remember we said that these are talking about a cosmological model and how the universe has expanded. And so this is a model in which the universe starts expanding, but it's decelerating in the expansion before dark energy takes over and it starts accelerating in its expansion. And this is one way in which the supernova data that were used to one of the first probes or identifications of the existence of the acceleration. This is one of the ways the supernova data are plotted. But now it's plotted using the standard rod rather than a standard candle. And so another nice consistency check is that the supernovae and the standard rod, whether they give you the same curve, standard candles and standard rods. Yeah? And so here it's plotted in that way, and you can see, the different galaxy samples, they probe a different range of distances from us and a different range of ages associated with the best fitting cosmological model. Yeah? So the idea again is going to be the constraints, the error bars across are going to get narrower, and as samples have more and more galaxies, we'll be able to make the width in redshift narrower, and so we'll be able to really do the tomography that I was talking about earlier. But this is already great progress, right? Because before we just had the CMB and we had the present. Now we can really map it out. Okay, so a key assumption is that, nothing, is that the Baryon distribution has this memory of what it was like when the universe was 14 billion years younger than today. And it's not clear that's a good assumption, right? A priori, gravity's gone to work, it's made galaxies. And so one of the things we need to check is that that's okay, all right? So we know today things move, and so we can ask, do the motions of these things, does that mean the baryons are moving, and does that mean that this signature is gone? Now, we've got a consistent story. The measurements showed everything is okay, but now we're interested in percent or sub-percent precision. And so we need to be sure that in the 14 billion years, things did not move enough to change the length of the rod by 1% or less. And so that's the concern. And we know there's structure formation. So here's a movie that shows you expanding universe, gravity goes to work, makes the smooth universe lumpy. Okay? Then those lumps all move, they merge with each other. Those are the galaxies that are going to be the galaxies we observe. Okay? So it's a messy business. And so it's a legitimate concern that the gas distribution should not have moved too much to make this, to invalidate this. And so here's now the way cosmologists would usually look at the expanding universe. They'll say, we know the universe is expanding, so we'll always divide out by the expansion factor. So we'll call that co-moving coordinates, and we'll ask, as we divide out, what does the structure formation look like? And so what you can see is that the structure formation is pretty local, right? You can see that stuff is falling in here, stuff is falling in here, but nothing is going from here to here. And so this scale here was 50 megaparsecs. The BAO scale was twice this. And so because nothing is moving across the box, that means the feature should still be there for us to see, and so we see it. But now we want to be sure that the feature did not shrink by 1% or expand by 1% as a result of these motions. Okay? The naive expectation is because what we're looking at are galaxies, and the galaxies are regions where gravity has pulled stuff together. The naive expectation is that that rod might have shrunk a little bit because gravity might have pulled it in. Okay? If we were using voids as the probe, and the voids are things that are expanding rather than contracting, then maybe with voids, maybe there will be a slightly different, the signature might have a different sign. Okay. But for the galaxies, we're expecting that basically it should be a small effect, but we want to be sure it's sub-%. What I have up there is just the back of the envelope calculation. If you're moving at 1,000 kilometers per second for 10 billion years, you move 10 megaparsecs. The size is 100 megaparsecs, so that means you're not going to erase a feature, but you will do some damage to it. So there is some memory of the initial conditions, pretty good memory of the initial conditions, but now we want to be much more precise about that, right? So we want to be sure that we're not changing by too much. So here's a same kind of simulation, but now we're highlighting a region where there was an initial shell. And gravity goes to work. And what you can see is that the nice clean shell, as time goes on, becomes wobbly. And so if I were to do the profile of the shell, it was a nice dashed line, and now that nice dashed line will have got smeared out by essentially random motions, okay? Driven by gravity. And so that nice feature got smeared out. That's one effect. But the effect we really care about is whether the net diameter of this circle is different from the diameter of the red circle, which is the starting diameter. Yeah, so there are two effects. First effect is what's the position, which is like the diameter of the rod, and the second is how easy is it going to be to measure it, which is how big is the contrast. Did it get smeared out completely? We'd like both to be undone. We would like a sharp feature at the original scale. Yeah? That's going to be our measurement. And so that's what reconstruction is trying to do. So reconstruction is trying to take the fact that today everything is moved a little bit from where it was initially, and we're trying to move back to where they started. Okay. All right. So I'm running late, and so I'm going to skip the next few slides where I say one of the things we could try to reconstruct is simply the statistic that we measure. So we can try to model the effect on the two-point correlation function or the power spectrum and try to correct for that. The other thing we can try to do is correct the entire field. meaning literally move the positions of objects back to where we think they came from and make the measurement then, okay, having reconstructed. So this is reconstructing the statistic versus reconstructing the field. And so I'll skip the reconstructing the statistic and go to reconstructing the field, which is the optimal transport. But if you're interested, you can ask me about the statistic later. So what do we want to do? We have a bunch of particles today. We want to move them back to where they came from. And there was an old problem in the 1700s, which was, here it's shown as a nice sand castle. How do you dig a hole, take the sand out, and make it into a pile? Of course, it was done for war, right? How do you build a trench most efficiently? And so the problem that we want to solve is very similar. Okay? We want to rearrange the particles that we see today to be where they came from. To do this, we need to have a rule. We need to decide what's the cost of going from one place to another, and we're physicists, so then we'll just minimize the cost. Okay? And so that's the thing that's optimal, is the cost. But of course, everything is going to come down to defining the cost. Okay? And so here's an example. If you have the 5 orange balls on the top, and you want to move the 5 orange balls one site over, one way you can do it is you can make each ball hop one site. The other way you can do it is you can make the leftmost ball hop all the way to the right. Okay, so those are 2 possible ways, 2 of many possible ways of doing this. Right? And so now the cost, well, in the top one, the cost is n balls, so the 5 balls each had to move one step. In the bottom one ball had to move 5 steps. Cost is the same. If instead the cost, so that means you can't tell the difference between these 2 rearrangements. If instead the cost is the square of the distance, so then you will be n hops, each of distance squared, versus 1 hop of distance n squared. And so now these are obviously not equal. And so your cost is going to determine which is the preferred way. We're going to have one additional requirement. And that additional requirement is that no shells can cross. So that means this guy actually can't cross this guy. This guy can't cross this guy. Okay? So in 1D, it means the solution is simply this. This all shifts. But in 2D, there's more complicated arrangements that are allowed, and in 3D, more complicated still. But so we're going to have to write down a cost, and we're going to have to impose that there was no shell crossing. No particles are allowed to go through each other. Okay. It turns out that if you do this, then that opens up a bunch of beautiful math that was realized in the early 90s. Okay. And that beautiful math says things like, when you solve this problem, you can write down a numerical solution that will be exact, and that will be optimal, and that will be unique. And so we're going to make use of that. One other way optimal transport is used, so in our case, we're going to be using it literally to move particles, to transport particles. But one other way it's used is to map one PDF to another PDF. Okay, so here I'm showing you a distribution of some variable, and you want to know, how do I transform this into this? And so optimal transport will give you a rule for translating this into a PDF of this shape into this shape. Meaning it will tell you what this value, if x is running from 0 to 10, what the value 9 maps to here, and so on. Okay. In 2D, this gets used all the time on the web when you want to morph images from one image to another. And here we're morphing Monge into Kantorovich. Okay, so how you smoothly go from one to the other. So we're doing 3D version of this. Okay. Let me start out with this problem as follows. So we start out saying that we think that the universe was pretty smooth to begin with. And we think that because when we look at the CMB, although it has hot and cold spots, those things are 10 to the minus 5 temperature fluctuations. So the CMB is actually pretty smooth. And so that means that we really think, and in the simulations that I showed you of structure formation, the simulations start particles on a grid. That's the blue dots. And then the simulations move the particles. And then at the final time, the particles are at the positions of the red dots. And so the uniform grid got distorted. And so our goal is to undo these distortions, is to move each red back to a blue. So when this problem was first phrased in this way about 30 years ago, then it was like a combinatorial problem, right? There are all the possible ways you could assign this red dot to all the other blue dots, and then this red dot to all the other blue dots, and so on. You apply the cost, you minimize the distance. You minimize the cost. That's an expensive thing. It's also not a very nice thing, so that's called the discrete optimal transport problem. But it's not very nice because, for example, we observe some galaxies. We don't observe all the dark matter. Suppose we observed 1/10 of all the particles, or 1/100th, 1% of all the particles. Then so the red guys that we observe, they would be very far apart from one another. The average number density would be low, interparticle spacing would be big. And so if we were doing the discrete problem, then we would be saying they each go back to a very sparse grid. And if the spacing of the grid is more than the typical 7 to 10 megaparsecs that we think particles have moved, then we will get an error just from the discreteness, and we won't be able to play this game. And so the discrete problem is not what we want to do. So we need to think of a cleverer way to treat this problem, both for computational reasons and for the simple fact that we're almost observing a sparse data set. So the nice step forward came from this paper here, which went as follows. So let's think of doubling the number of blue. Okay? Now we want to know which blues are closest to the red. And now we can double the number of blues again and ask which blues are closest to each red. And we can double again, and we can double again. So in the continuum limit, you can ask, well, what is the set of blues that are associated with the red? What is the set of blues that are associated with this red? And we'll partition space into all the regions that are associated with each of the points we actually observed. Okay, so this is a way of partitioning space. And our rule for partitioning space, so people have thought about how to partition space quite a lot. Perhaps the best well-known one is called the Voronoi diagram. The Voronoi diagram would say, you go to each of your points, the red dots, and you ask, what volume is closest to this red dot than to any other? And so now you make your cells. So if you do that, then what you'll do is you'll get cells that are different sizes, each with one particle inside. So because you've done that, that means the cells all have very different densities. But the problem we want to solve is we want to go back to the case in which there was uniform density. So what we want is to solve something like this Voronoi problem subject to the constraint that all cells have the same volume. They may all have different shapes, but they have to have the same volume. And one way you can think of doing this is start from a Voronoi and start making the small cells bigger and make the big cells smaller and iterate. And so the computer science guys figured out a nice way to do this that's fast. Okay? This tessellation, instead of the Voronoi tessellation, is called the Laguerre tessellation of space. And so that's what we're going to do. So the Laguerre tessellation is same volumes. And once you've done the tessellation, then you can say, well, so I had my red dots, I've done my tessellation. Now each red dot is now surrounded by a blue cell. What is the barycenter of the blue cell? It's not where the red dot is. It's some other position. And so that we'll treat as the initial position of the red dot. And we'll say the red dot started from the blue and it moved. Okay, so that's going to be the algorithm. Okay, so you make the Laguerre cells associated with the point distribution, and then you use the barycenters of the cells to tell you the displacement. Okay. So here's an example of how that works in a simulation. We see the type blobs. These are the dark matter halos that have the galaxies, and we reconstruct by making the Laguerre tessellation. We'll reconstruct making the Laguerre tessellation, and we'll see, that each of these blobs came from a bigger region in the past, purely from saying we had to do this Laguerre cell trick, right? The Laguerre decomposition knows nothing about gravity. The only rule is that you had to make uniform cells. And so in this sense, the algorithm is working with an assumption that is independent of cosmology, that the initial field was smooth. So it doesn't matter. And if you modify gravity, it doesn't matter. Most models will agree that the initial field was smooth. Okay. And so it's made no extra cosmology assumption. So it's an attractive approach. Okay. And basically, this paper by Brenier, so he's the father of the field, is applying it to cosmology here, the formalism, and now with the semi-discrete algorithm with the Laguerre cells, it's fast enough that it's feasible. But there's one trick, okay? And the one trick is the following, that we only observe galaxies. We don't observe all the dark matter particles. So we only really observe, let me skip this, and I'll come back to this in a second. We only observe, light, and the light is just the tip of the iceberg, right? We're not seeing everything. So because we're not seeing everything, we have to ask, the subset of things that we see, were they uniformly distributed in the beginning? And we know that they were not. Okay? It's only the full matter distribution that was initially uniformly distributed. We can see that in a simulation. The subset of things that we do see, they were not. So there's a beautiful math problem that has not been solved that would be nice to solve, that currently we do a hack, but let me try to state the problem. And the problem is the following. We think that the places that we do see stuff are the places where the divergence of the velocities is bringing everything to a point. So if I imagine I have a flow field, and my flows, there are some places where I have net inflow from all directions. Supposing I only saw those positions in the field, and I didn't see the others, can I reconstruct the full field? So that's the thing we'd like to solve in optimal transport. Our current hack is to make a guess for how matter is clustered around the things that we do see. Okay? Because we haven't solved the beautiful math problem. And so we make a guess of the stuff that we call dust. So we have to guess how much dust, and we have to guess how clustered it is around the stuff that we did see. And so that means that now we have to make a little bit of cosmology assumptions that we have to do. So it's no longer cosmology free. So that's taken away some of the beauty of the approach. But we're going to do this. And one of the things that I'm hoping will work out longer term with with Enzo's group here is to make better models for the dust so that we can make the OT approach work as we need it in the future. Okay. And so let me quickly show you some pictures of how well that works. Let me go back, go to a few of these guys. So, if we start with an initial evolved set of objects, and we run we make our guess for the dust, and we run back in time, and then we say, so what was the clustering signal of these guys in the past? Then we get this. Okay, so we get a new clustering signal because they were clustered. They were a subset. The full field is not clustered by construction, but this subset of particles is. And we can compare it with the actual answer in the simulation. And we see that we reconstruct the actual positions very well. Yeah, so the algorithm works if given a good model for the dust. And the other nice thing that we see from this is that the reconstructed shape correctly reconstructs the positions of objects, but the signal has a slightly different shape from the shape that people think the signal should have if they could see the full field. Okay, so the algorithm didn't know anything about the fact that we see a biased subset of tracers. The only thing it's saying is we have to get back to the uniform field. And it is correctly giving us that the subset that we're using is clustered slightly differently from the rest of the field. And it's getting it exactly right. And we're going to need this level of precision for the next generation data sets because, if you try to fit this model to this data, you will have a problem. And so the optimal transport is a nice way of getting back to the answer with higher precision than other methods currently can. Okay. Importantly, we think we have some understanding of why this shape is different that I won't get into here. I mean, you can take it as a thing we've seen in simulations, but we actually have a theory model for why it's that way. And so it's kind of a nice self-consistent story that we can get. There are other consistency things we can do. Instead of measuring 2 points, we can measure 3, 4-point statistics. I won't get into that. I'll just go to the final slide. And so I had some stuff about different directions that you can go. So we can do this. In the future, as we get more data, we will also get information about the speeds of objects. Because right now, our starting point was just the positions of the objects. So if we also have some estimate of their speed, then that helps this approach. And so ongoing work is to make the synergy with the kinetic SZ Sunyaev-Zeldovich effect, which will measure the speeds of objects. The other thing we can do is the CMB is slightly lensed, and it's nice to figure out what the unlensed CMB was. And optimal transport is a nice way of doing that because the photons traveled in straight lines, and they didn't really cross. And so this is the right framework for that problem. There's a nice coincidence for the problem that gets solved. So we had to minimize something to make the Laguerre tessellation. The Laguerre tessellation, there's an action that you minimize. The action that you minimize is the same action as Fermat's principle for the gravitational lensing problem. So the gravitational time delay of a photon is due to, photon has to take 2 paths, so there's 2 geometrically different lengths for the image to reach you, and there's a GR component to the delay from one path compared to another. And so in optimal transport, if this term was 0 or was the same constant for all objects, that would give you the Voronoi tessellation. This one being non-zero is giving the Laguerre tessellation. And so optimal transport might be a nice place to apply time delay Hubble constant estimates because that is a data set that's going to grow by times 100 in the next 5 years or so. So I'll leave those there and just say there's a picture of the lens CMB. but because I'm late, I'll stop with just a quick statement that OT has the potential, the optimal transport has the potential for being able to deliver what we need for the next generation data sets, especially if we can make better models of the dust, or we can solve the OT problem where the tracers, the subset of the field that you see, are the ones where the divergence is highest. Yeah? So it's a very well-defined math problem that needs to be solved. Okay, thanks for your patience. Sorry I ran late. Yeah?
I wonder, so okay, I work mainly in particle physics accelerator, and we have models that we use for unfolding problems, Monte Carlo models, and sometimes for getting from data to the truth level comparisons, we have several models that we compare and we evaluate uncertainties out of it. Do you have some approach similar also in this case, beyond just the statistical analysis? What is the uncertainty associated to that can be maybe, at least for us, sometimes it's a big effect that we need to take into account.
So, yeah, so we'll do, what we'll usually do, so you can see that on any of these things, there were like error bands, right? And so those came from making many realizations of the experiment and running the pipeline and making the measurement. And then what will happen is, so we'll get the bands from doing that, and then we'll paste on here what was the measurement in the data set. So
it's kind of a sizable band, indeed.
Yes, indeed. Right? And so the size of this band will now depend on the data set, right? And so if we probe bigger volumes, as we will in the future, the size of the band will shrink, and so on. But I've only answered half your question, right? So you could ask, okay, so this is what we got from doing the optimal transport reconstruction of the problem. But because it's not the full story, it might be a good story, but it would be nice to have other algorithms that also do this to make sure we got a consistent story. So there is currently an algorithm that is the current standard that is not able to reach this level of precision. But no doubt in the next few years, they will work on getting that one better, so there will be another approach. And then ENSO has a nice method that's much harder, in the sense that this one is minimizing an action, but the action was particularly simple. And the minimizing the action was simple because we care about the start and the end point. We don't care about how you reach there. ENSOs will actually minimize the action as you take steps along, and so instead of just the net displacement, you can also solve for the velocity along the way. Yeah? If that gets fast enough, that's yet another way to do this. So, yeah.
Fantastic. I think we're running a little bit late, so let's keep asking questions to Ravi over a small refreshment here, and let's thank the speaker again.
Sorry?